Hello, welcome to the class, and let's begin our today's content. Last time we have talked about the joint distribution, which like two variables, we consider it all together at the same time. But we only considered the discrete cases last time. So today we are going to move to the another type of random variable, which is called continuous random variable, and how its joint distribution will look like. So this will be our main topic today. And we'll slightly talk about some examples about how to use the independence, how to calculate expected values, and how to do the sum of two joint distribution together. And that will be our main goal today. So first, we just to get a recap of what joint continuous distribution is. So joint continuous distribution, you can view it as like a 3D, three-dimensional graph. Because remember, when we talk about distribution curve for a single random variable, it is just we recognize it as the area under some curve. Oh, like for example, there's a curve here, and we just calculate the area below it. So that will be one-dimensional simple random variables distribution. But for joint distribution, the continuous one, well, it has two-dimensional or more dimensional, but if there's only two random variable x and y, it's easy for visualization because if there's three or more, we cannot easily to draw a graph about that. So we will use x and y, the two joint distribution as one example to help you understand it. So in this case, there's one curve at the y dimension here, and also there's another curve at the x dimensional here, which is here. So we can build some like accumulation of you can consider it as a volcanic cone or some other form of three-dimensional volume. And now the probability will be the volume under this surface. You can see it's now volume, no longer a two-dimensional area. So it's the volume below the surface and above the zero plane. So that's the probability when we consider some rectangle A1 to B1 and A2 to B2. So those are restrictions about what portion we want to get. So yeah, so the volume under a joint distribution of F under, for example, this is graph, you can see is from from the x dimension is negative 0.5 to 1, and the y dimension is negative 1.5 to 1. So that's the example of how joint continuous distribution of looks like. Okay, and now we go to a more rigorous definition of that. So we always say how we can use a formula to calculate the joint distribution function. So it's easy to see. It's easy to see the first definition. Like, what does it mean? It means like all of the random variables x1 to xn, they are in a certain range, like the rectangle. Or more dimensional is a n-dimensional rectangle, but still a rectangle. So we will say the probability of those those x, y, z, or a, b, c, d, they are in such rectangle. Or so when you say the probability, they're within this one. And now we are trying to figure out we can use this notation or we can use this notation too. I think to this point you can easily understand what this character means. So how to calculate it? We just do multiple integrals. So if you have learned about multi-dimensional integration, this will be very easy to understand. There's a function because f now is a function of n-dimensional, like from Rn to R. So this one has n variables here, and we do the integration of all of its variable one by one to calculate this joint distribution. So that's about it. Okay. And there's some like very obvious fact about this formula is like if the R is not a rectangle, it's just like a whole volume of things, it's the universe. So what will happen? So so all of the integral is going from negative infinity to infinity. And in this case, well, it's one because the probability of all of the joint distribution sum up is one. So which means like the volume, if the volume below the surface and above the zero plane, we have no rectangle restriction, like for example, here is from negative infinity to infinity, and here is also from negative infinity to infinity. So what happens is like it will calculate to be one absolutely. All right. And another thing is like all of this fx or fx1, x2 to xn is all above zero, which is larger or equal to zero. All right. So that's the some basic properties or very easy observations. And also like we can using major theory to understand what is actually integrable means. But yeah, but we have not touched about major theory yet. So if you are interested, you can search about what is integrable and what function is not integrable. But now we can just understand like if a function's boundary is continuous and piecewise differentiable, it is what we call integrable. And well, most of the case, I think 99.9% of the case that we meet so far, it is just like differentiable and integrable. Okay, so that's it. And let's see some examples of joint distribution. So one easy case is what's the joint distribution of want to find out like, okay, so there's two random variables now, x and y, and we'll consider its joint distribution f and the joint PDF f, which is small f. So if we can know the f, remember how to get a small f, how to get a PDF. So from CDF to PDF, we just do the differentiation once regarding the corresponding variable. So that's what we do it. So how about compute this one? So remember what this one is. This is just we want to do a PDF, like a PDF of joint distribution, right? Because this one is this one, and it will become this one. So this is not well, we say, yeah, it is not a CDF, but it's not a PDF, but a CDF of in the R, in the region R or in the rectangle R. So how can we do that? And R is from A1 to B1 and A2 to B2. So so first we call if there's only one variable, what we can do to calculate P from A to B. So we just do the CDF difference between two CDF goes from B to A. So like here, if here's B, there's A, and we just like first calculate B is from like 0 to B, it's going from this curve, and A was A, it's going from 0 from A here. And we just cancel the A term out, we'll leave in this region, right? We leave this area. So that's how we do the computation of the probability summary. Well, in this case, there's two-dimensional, so how can we do it? First, we do the upper layer. For example, we can do something like that. Let's draw something. Okay, so this is two-dimensional. This is X, this is Y. Okay, and here's some, we can say, well, yeah, so this is B2, this is B1. This is A1, this is A2. So we want to figure out this rectangle, right? We want to figure out this rectangle. So first we just do the probability of like it's oh wait. So this is B1, B2. Okay. So exactly, yeah. Maybe, yeah, this notation is a little bit weird. It's not A1, A2, but here is B1, A1, right? A1, B1. Huh, okay. I think the formula is right. So this is A1, B1, and this B1, and A2, B2. Is this right? So this is the first dimension and this is second dimension, right? Which is like we calculate like this is the interval and this is the interval. So that is right. So that is A1, B1, A2, B2. Okay. So first we calculate the distribution of all this area of B1, B2, and we minus what we minus out is B1, B1, A2, which is going from B1 to A2. So we minus this region out. And then we also minus the B2 to A1, we minus this region out. And then what we found is we left this region not minus out, but we minus this part twice, so we will add it back. So what we do in the end is like we're doing, okay, wait a minute. So what we left behind is we minus the two terms out and we add the A1 and A2 back. So that's how we do this this problem. Okay. Okay, so let's see the next one. Uniform distribution is very common in discussion of the distribution examples. So here I want to introduce some very interesting definitions of union distribution. So union distribution is like, well, it's very union. It's very it's the same distribution of all of the rectangles, right? So we define union distribution on the dimensions of in the like the two-dimensional interval as if the region is in I, then it's 1 over I, and this absolute value here means the area. So this is area of I. Okay, this is the area of I. And if it's not in it, absolutely it's 0, right? Okay, and this one can be written as this form. What this form is, what's the 1 here means? 1 here means this one. 1 here means if it's in that region, it's 1. If it's not in that region, it's 0. So this is the condition. So every time we see one some area or some or some values, and this is condition, like if the function is this condition satisfied, then it's 1. If not satisfied, then it's 0. So this is how this this question is mean here. Okay. So so this is our definition of the uniform distribution. So why does this make sense? Because remember the whole probability of some distribution function is 1, right? So if the area is like 100, then we need to set like 1 divided by 100 to mean like every unit it has 1 over 100 percent probability. So that will make us clear and satisfy the basic property of the distribution function. Okay. And also, so let's first assume that xy be a uniform distribution over the unit square, going from 0 to 1 square. Okay, and what's the area of this region? It's just 1. It's just 1 times 1, which is 1. Okay, and we can see we can go from this is our how to say the PDF, which is the distribution function, which is a density function. And if it's going from 0 to 1, well, the region is just 1. So there's no way to, because the I area is 1, so it's just 1 and 0 as our like the PDF. So that's a conclusion. And now we want to find out the probability of x minus y is smaller or equal to 1 over 2. And this, how to represent this idea, we can use the geometric idea to do it. So first of all, we can calculate the inequality of some absolute value, which is x minus y's absolute value is smaller or equal to 1 over 2. And this will give us some clue about it. So we can figure out 2 functions out. First is y is larger or equal to x plus let's say it's x minus 1 over 2, which is which is this area, above this line. above this line. Okay, and also some cases will be like and some other cases will be y minus x smaller or equal to 1/2, which is y smaller or equal to x plus 1/2, which is this line. So it will go down. So it's in the middle. So this is the region we want to find out. And because it's uniform distribution, then all of its distribution is the same. So we just want to figure out what's the proportion of this region regarding the whole unit disk, which is not unit disk, but unit square, which is area of 1. So in this case, we can just simply calculate the region. We just minus these two small triangle out, which is a square of, we add them together and it becomes a square of with size 1/2. So that will be 1/4. So the region in the middle is 3/4. So that's our conclusion here. And that's the probability of we can find that satisfy this condition. Okay, so let's generalize this idea, because here we only use like, what about x minus y is smaller or equal to 1/2? And 1/2 is a fixed value, but it can also be a variable. It can vary. It can vary from like negative infinity to infinity, although some values are not very meaningful. So here we'll generalize these computations. So what is the probability that x minus y's absolute value is smaller or equal to t for all of the t, for all of the t which is a real number? So the first case is if t is smaller than 0, then what will happen is like if t is smaller than 0, well, so in this region, for example, we'll figure out some cases like if t is minus, for example, t is minus 1/2, and what will happen is we'll find these two lines is the same line. These two lines is the same line. However, what we're going to find out is we'll find the probability that goes this way and goes this way at the same time, which is 0, which is impossible to figure out. So in that case, we say if t is smaller than 0, the probability is 0. And what about t is larger than 1? So larger than 1, it means like the line becomes not 1/2, but goes like that. But it's beyond 1, beyond the y equals x plus 1, or go beyond y equals to x minus 1. And now we're trying to figure out the probability in the middle. And what that is absolutely 1. Because if it's going to the middle and it covers all of the square here, right? Which is 1. So the only meaningful or the value that is interesting to discuss is when t is in the range of 0 to 1. So we can define this region as how to say, we can say, well, we can define it as xy, which is x minus y smaller or equal to t in this region, and we're going to discuss that. And then we can figure out, well, we can figure out if t is in the range of 0 to 1, then there's two lines which is lies in the region of the square, and we're going to find out the middle value, the value in the between them, right? So in this case, we can say, or what we can say about this, we can use our discussion about above here to generalize it, which is we can calculate 1 is some 1 value minus 2 times the triangle's value, which is how to say, is 1 minus t squared. So our conclusion will be 1 minus t squared. So that's our generalization. So let's go above to discuss why we want to discuss this example. What's the connection of this uniform distribution with the joint distribution? It is just because it has two random variables, x and y. Like here, we have x and y, and we will discuss, well, what will happen? What's the probability that x and y together satisfy some situations? So that's how we do it. So that's why it's a joint distribution, not a very simple single random cases. So that's the difference. Okay. Yeah. And what's about, so here, what we can discuss is we calculate is probability. from cumulative density function. And what about the PDF? We do what we'll do is we do a differentiation of that. So this is our CDF, which is like if smaller than 0, 0, larger than 1, 1, and between them is this function. And what about the PDF? We do the differentiation, and then we figure out this form, right? And otherwise, 0 and 1 is just 0. And this can be computed as 2 times 1 minus t. And so what does this mean? This graph looks like that. It's all 0 when it's all 0 when it's like below 0, and when it's actually at 0. And this is 1 minus 0, which is 2. And then goes to 1, and then goes to 0 again. And you may say, well, this looks very weird because there's a jump in this area. So how can this happen? So remember, like the PDF is the trend that the probabilities happen. When it's like very high, it means the probability is increasing very quickly, and when it's very low, it means the probability is increasing very, very slow. So, like for example, if it's just 0, then the line is here, and we just move a very slightly area, the region will increase very fast. But when it's close to 1, like the line is here, and you increase a very small area, increase a small distance here, the area will increase very, very slow too. So that's why like when close to 1, the probability density function becomes very low too. Okay. And yeah, let's see another example. Another example is about the exponentially distribution of the joint distribution. Okay, so we can say there's two x, y, they're exponential randomals. So fxy is equal to e to the power of minus x plus 1. So this is a joint distribution because we can see there's a function of x plus 1 replacing what can be x here. And because it's exponentially distribution, it's exponential random variables, its domain is going from it's only the not positive integers, positive real numbers, which is from 0 to infinity. So that's why we do some how to say this function? It's called identity function. No, it's some like indicator function. Yeah. So the indicator function is here. It's to indicator function to restrict the area that we can choose the probability from. Okay. So what is the probability that x plus y is smaller or equal to t for t is greater or equal to 0? So this is our question. We want to find out like when t is larger or equal to 0, which makes this probability make sense. And they're both smaller or equal to 1, both smaller or equal to t, just sum. So our idea is to find out the region with x, y greater equal to 0, and their summation is smaller or equal to t, which is a summation problem. Okay, and what we can do here is we can replace one of the term out. We can replace, we can just remaining x, and y becomes t minus x, and that's our solution. So we can remember we can like this is our beginning, this is our beginning here, and we just replace it here, and then we do it here, and we do it here. So yeah, this is what this step do is we do a integration over y. Because there's only one y, we can integrate the y out, and then integrate the x out, we can reach this point. So the solving of the integration of multi variables is just doing from the inner layers to outer layers one by one, and we can do it. Okay. So we can figure out CDF and then do integration again. We do this, no, not integration, but we do the differentiation again from this point to this point, and we are reaching the PDF. Okay. So next one, we talk about the marginal distribution. So what we talked about above is how the joint distribution works, and yeah, and some example of how we calculate its probability. And now we go into another similar concept in discrete random variables, which is marginal distributions. So let x and y be two continuous random variables with the joint probability density function f x and y. Then the marginal is like when we want to find the marginal probability of x, we do the integration only by y. And similarly, if we want to do a marginal density of like a marginal probability of y, and we integrate by x. So what's the meaning there? It's very similar to discrete cases. It's just like, well, when we have many cases of x and we sum them up, or very similar to like we do the integrate of all of the x condition, and we will concentrate it into the y to make y readable. Right, so that's the intuition of doing that. And this is the two random variable cases. And if there's more cases, we can also generalize that out. So for example, if x now is not one random variable, but it's k random variable, and y is n minus k random variable, which sum up to be n variables together. And we can, suppose we met a problem that we want to find out what's the marginal density of many x, like the kx altogether. Then we just do the integration over j1 to yj n minus k. We just do them to replace the dy here with all of the those random variables, and we can figure that out. Okay. So let's see one example of the uniform distribution on a triangle. So, okay, so first, what triangle are we talking about? Triangle is this triangle, is all of the region in the unit square. However, there's one condition. There's like x is larger or equal to y. So only in this region, x is larger or equal to y. So this is a triangle. And first, we can calculate the area of this triangle, which is 1 over 2. So that means like the 1 over the area of this triangle is 2. So by the indicator function written form of the uniform distribution, we can write out, well, this region is 2 if 0 is smaller equal to y, smaller equal to x, smaller equal to 1. And this region is 0 otherwise. Because, well, if it's not in the region or in this region or some other region outside, there's no probability that the case will occur. So how can we figure out this uniform distribution? So first one, we do a case 1. It's like x is in this region, it's from 0 to 1. And what we can do is we can do fx as 2 times the formula. And how can do the integration of this one? Because this function is only possible within the range of x is between 0 and 1. So this is just 2. This is just 2. So yeah, this is just 2. And if we remove the 2 out, so it becomes 1. So it's just like going from 0 to x, 1 dy, and this is 2x. And case 2 is like if x is greater than 0 or x is smaller than greater than 1 or smaller than 0, then the x-axis go beyond this condition. It's here otherwise, so it's 0 in the middle. So the integration of 0 is also 0. This is so that is the case. So we combine this together, we can find out like the marginal of x is 2x, and the marginal density if like x is not between 0 and 1, and it becomes 0. So that's how we do the marginal distribution on some joint distribution functions. So lastly, we can see some other useful formula like this one, which is the transformation formula. So remember before we have talked about when we talking about the expected value of some continuous random variables, we say, well, we can if the expected value have some, it's not the random variable itself, but with some function g of some random variables, then we can just times the function itself with the density function and then to figure out its form, right? And this is very similar. This is very similar, although there's more random variables occurs in the function g. However, we can also do a function g times the function of the density function of n-dimensional and use the integration to calculate it out. Okay, so we can see example. So this example is the geometric example too. It's also a geometric example. So mainly the like the example people give in drawing distribution is all geometric. Okay. Because like geometry, we can deal with two-dimensional or even three-dimensional in a very clear form. So this is so in this case, what is G? What is G here? We can use like the area. So it's like the side times another side, which is x times y, right? So this become our G function because what we want to find out the expected area. And expected point is all the possible points within this range, which is a uniformly distributed form in this case. And just to notice, this triangle is different from the triangle in this case. This triangle is here, but this triangle is in a symmetric form regarding x equal to 1/2. So the function is changing. The function changed. It changed from so now the function becomes x plus y smaller or equal to 1. So that's so this is our new function right now. So what is the area of the random rectangle R on average? So the first step we will do is the expected value of the certain range. So this range will be will compute the expected value of something. So the expected value is here. The expected value, we just want to figure out, the R here doesn't represent some absolute value, but it's just like the function, which is the area. So that makes me confused at the beginning. So once we know it's the area, we can use the side times side to figure it out. Okay. And we can denote this by G and remove to the G function times the density function here. And the density function here we already solved is, although the triangle is changed to another side, but the area is the same, which is 2 times the indicator function here. And what we'll do here is we can separate the 2 out and we can replace the indicator function with here. Yeah, with here. So now x is smaller or equal to 1 minus 1, right? So so when we first calculate integration of dx over x, we notice its boundaries is like between 0 and 1 minus 1. And we do it out, we can figure out it's 1/12. The next main topic is regarding the independent continuous random variables. So the continuous random variable x and y are independent if and only if this is if their joint distribution is equal to their marginal distributions product for all of the x and y in the range of real numbers. So why is that the case? We'll prove it later, but we can first generalize it to more like common cases, which is there's more random variables, like there's n-dimensional random variables, and in this case, like we can going from like fx1 to fxn, and it's like we can times them all together. So it's just expanding the joint distribution to more cases. So this is one generalization. And the second, we can also do the transformation here. It's like, well, there's like S1 to Xn, and they're independent. And we can also do some maps, some functions over these random variables. And well, no matter what function we act to them, even like different function to different random variables, their result will also be independent. So that's the second generalization. So we can prove the if and only if relationship here. Y if this is satisfied, then X and Y are continuous random variable. And we can prove the two random variable cases, and then we can make the generalization one to make it for all dimensional cases. So first we can do some so in the first case we can use some knowledge that we already have. Is for the first one here is for simple random cases. If X and Y are independent for all intervals I1, I2, in interval I1, I2, and then the probability that both satisfied is equal to their product, is equal to the probabilities product. So this is the first one. And the second knowledge we have before is the definition of the joint distribution, right? So the probability, the distribution of X in interval I1 and Y in interval I2 only equals to the integration of I1 I2 over X and Y dimension. So that's the two knowledge we had before. And now we'll prove the first factor. So first, we already know like the X and Y, the two random variables, they are independent. So what we'll prove is like we know this case, and then we'll prove this case. We'll prove this equality is satisfied. So we can use our first knowledge. Our first knowledge here. It's like, well, this condition is equal, and we can figure out this one. This is equal by their independence, because independence now become our assumption, right? And this one, what is this one? This is a continuous random CDF. I can write it in an integral form. And for Y random it is also continuous, so we can write this form out too. And if you are notifying like these are two integration over fx and fy, right? We can use the Fibonacci rule to write the two integrals in the beginning and write their integrals part in the middle too, and we reach this part. And also from the second knowledge we have before, which is here, and what we can know about that is like, well, this one, what is this one? So this one is this one we can like this one is also equal to this case, right? It's also equal to this case, and this case is equal to this case. And the only difference between them is this is the product of two single random variable functions, the PDF, and this is the joint PDF. So they are equal, and which is satisfy this one, because the single random variable function here is also the here you can see here is also the margin. We can also consider it as the marginal density when we do from the joint distribution. So we are done. And the second dimension is very similar too. And the case is we already assume that we know this is true, and we'll prove back that X and Y are independent. So this becomes our assumption, and this sentence become our goal for the proving. So in the first case, let's fix some arbitrary intervals, I1, I2. Okay, and the probability of this happening is this one. It's from our knowledge too. And the assumption that the joint distribution is equal to their marginals product, we'll use it here. And separate them out, going from I1 with Bx and I2 with Y. And this become the product. And then from our knowledge one again. So what this is, or what this is this one. It's the joint distribution one. So now we have proved like, well, this one equal to this one. So they're independent. So we have done proof. Okay. And there's another example. This example is the minimum of the IID random variable. IID, remember, is called the identical independent distribution. So let's say this example altogether. And the first condition is there's x1, x2 to xn independent continuous random variable with the same distribution f. And we want to find the PDF of V, and V here is the minimum of all of these random variables. So by the first second, you might wondering, one special case is like all of them are independent. So their minimum, it must be themselves too, because they're same. They're same. So it's same. It's just like the minimum is also x1, right? But well, and this imagination might slightly be wrong, because even they are identical, they're not fixed value. They are maybe because they're vary between 0 and 1. So what this here find out is all of the cases they are varied behind some value. So we can use a diagram to show that. For example, this is x1, this is x2, this is x3, this is x4. They are all going from 0 to 1. And they might locate in different cases. For example, x1 is here, x2 is here, x3 is here, x4 is here. So the minimum is what? Minimum is this value or this value. They are very similar. So the minimum is at this case. So this is our V. V is the minimum of those, not equal to any of this one. Maybe equal to one of them, but not equal to x, because x, the expected value of V is here, but expected value of x is here for uniform distribution, right? So that's why they are different. So the minimum, the minimum of like n IDD random variable is not their value. Okay. So let's figure out its PDF. So the first step, we'll do a CDF. Because CDF is always easier to discover, we can just do the small or equal to some fixed value to figure out it. So the CDF of V regarding T is equal to the probability that V is small or equal to T. And this is for all, within all of the xi, and I is from 1 to n. Xi is small or equal to T. So that's the minimum. And this one can be represented as for all of the xi is larger or equal to T, and 1 minus it, right? And now we can use the independent property, is that this one is equal to x1 larger equal to T, x2 larger equal to T, and xn larger equal to T. Or we can write in another form, like x1 is in the range of T going from T to infinity, and the same condition for x2, x3 to xn. Right? And because they're independent, the probability of all of these cases, we can do a multiplication of all of its marginal distribution, which is here. So it's 1 minus this form. Okay. So this one can be this one can be solved. And also in another case, we are doing some larger equal to, but for CDF, we are doing smaller equal to. So we are also doing 1 minus P x1, x2, xn smaller or equal to T. So we reach this step. Well, and then we use the identical condition again. So all of this one is the same as ft because they are IDD. So all of the x1, x2 to xn, their this value is ft. So there's n ft together, so it's 1 minus ft to the power of n. And don't remember to add a 1 minus at the beginning. So that's the CDF of it. And what about if we want to find a PDF? Well, PDF is, yeah, it's just like do a differentiation once again. So we reach out the d dt f vt, and we do the integration. We do the differentiation, and we reach this 1 million. So that's the example of the minimum of identical distributed distribution. Okay, so yeah, so that's also one example of how the independency is used in uh in some like reality cases. Then we'll do then we'll do mm, another theorem, which is the convolution. And convolution we'll talk about more in the next series, but here is one example regarding the independent and the joint distribution too, because convolution needs two variable at their as their like prerequisite, and those two variables is one depending on another, or they can be independent too. So this is a joint distribution because we are viewing two random variables at the same time. So let x and y be two independent continuous random variable with the PDF f and g. Then the random variable z equal to x plus y has PDF. So what's z? It has the PDF hz equal to this one or this one. Well, you may say this makes sense because we just because z is equal to x plus y, then x is equal to z minus y, right? Or y is equal to z minus x. So it's actually makes sense. And the proof is very easy too. First of all, remember the prerequisite in this theorem, in this convolution theorem is like x and y are independent. So the first step we can do is we can separate the joint distribution into two marginal distribution in the first step. And then we'll expand its idealized or like not real integration into real integration, which go from like or indefinite integration into definite integration with fixed value from negative infinity to t minus y and a negative infinity to infinity. So this is our third step to get rid of the indefinite integral. And then we can do it one by one. We can remove the x by z, and we'll reach the final form. So that's why that's our formula for the convolution. Okay, and the last example is regarding sum of independent normal distributed random variable, and this is the example of convolution. The computing cases might be very difficult as illustrated, but you can also have fun to read it when you have time. So some of the basic idea is using the formula here and to calculate how if their mean is both zero and the variance is sigma x and sigma y squared. And then the mean, or yeah, the mean will not change, but their variance will be the sum. So this process will be the computation process. Okay, that's all for today.